Hi, this is Terry Dennery of the MathWorks. Um, in this presentation, we're going to talk about controls and predictive maintenance. Okay, and so the example we're working with here is a little device that essentially pushes packages off of a conveyor belt. Okay, and I might kind of get into the model right off the bat. So here's the Simulink model, and I'd like to begin by going into the controller, right? And the controller is really important, you know, part of all this predictive maintenance. And I want to kind of describe it from the point of view that everything inside this block, you know, can and often is put onto embedded processors, or PLCs or whatever it is that you're using. But essentially, it's done because all this can be converted into C code, C++ code, VHDL or Verilog if you're targeting like FPGAs or ASICs, or it could be structured text, which is a means to get it onto, you know, I think all of these commercially available PLCs. Okay. And so what I'd like to talk about is some of the signals that are being used in this controller, right? And so I think most of us are familiar with PID controls, and you kind of see it right there. Well, the basic idea is that you know how you want this device to turn. You know the angle at which the motor needs to drive this for it to essentially push the packages. So that's the angle command, and we compare that with the measured angle, and we get the angle error. That PID operates on that angle error to apply what I'd call a feedback request for additional torque based on how much how much error there is. Well, the overall torque requested by the controller has a little bit more than just that. So here's what's going to be requested and essentially delivered to our motor controller. Okay, and so there's this piece right here called torque FF. That's the feed forward torque, right? And the basic idea of this is that we have a model of the mechanism, right? It's very informed on the geometry and the mass properties of the parts that make up that mechanism. And therefore, if you can provide it, that same command for motion, that it can calculate the ideal torques required to make it move the way we want it to. Okay. And so anyways, let's look at the data inspector. Okay, so up here, let's look at the commanded angle and let's compare it with the measured angle, right? And that's what you want to see. You want to see them overlapping perfectly. And, I've worked with enough customers doing this. I know that this happens, very frequently. This is very real. Okay. And so anyways, these look really good, and it's always a good idea to go ahead, let's measure the difference between the two. We're going to see that the error, the angle error, that signal, that's the difference between the two, that it's nearly zero. Okay, so now let's look at the torque side of this. So on the torque side, we got the commanded torque. And we see that big old request for torque when it encounters that bigger package. Much smaller request for the smaller pink disc, which weighs a lot less than the rectangular box. Okay, but that's the commanded torque. All right, and let me show you the torque FF. So again, pretty much overlap between what's commanded and what's estimated by our feed forward algorithm. And that the torque PID is to account for the differences and essentially is operating on a near zero signal, and therefore it requests minimal additional torque. All right. Okay, so now what I want to do is introduce a failure. Right, and so I'll go in here, and you'll see I created a couple of failure mechanisms, and we'll get into this in a few minutes too, but there are three of them. One is the belt gets corrupted, meaning it gets sticky, and then there's a spring that kind of assists in the actuation of the device. All right, so we'll get into that in a second. But let's go into the motor, and let's set this motor factor to 0.5. And so think of this for right now essentially is that we've just reduced the capability of that motor to deliver to torque to about 50% of the level it would be, as a brand new motor, right? And we'll probably talk a little bit about, how this happens and why it's a real thing, right? But let's run the simulation again now. Right, so let me stop this animation. I'll hit the button up here and it will now recalculate and reanimate as the calculation takes place. watch the scroll bar as this starts moving. The design of this is to show it in real time, and every now and then it'll slow down. And that's basically where the calculation probably takes a little bit longer than real time, right? But most of the time, the gray bar is ahead of the scroll bar, and we can kind of see that most of the time it runs faster than real time. It's mostly during the interactions with the packages it slows down. There we go. All right, so now let's get back to our data inspector, and you'll see that our choices we made earlier are now being applied to the most recent simulation. All right, and what we're seeing here was the introduction of that motor error. The things actually begin to look a little bit differently. You can kind of see it in the comparison that there is a difference. At this point, I generally like to remove the angle command and the angle measurement, and you'll see that that error will rescale itself, and you'll see that our maximum angle error is about 1.5 degrees. And this kind of brings up kind of a really important point. Okay, and we kind of saw this when we looked at the animation. So that even with a 50% reduction in the capability of that motor to produce torque, um, that it all looked like it was working pretty well. And in fact, it was working very well. And the controls can be like magic. And one of the really magic things that controls do is that they make bad equipment actually perform quite well, right? And so I want to kind of explain that a little bit in this example. So with the reduction of the motor capability, well, there is a little bit of a lag, and that might be what you would say is expressed by this angle error, right? So the PID controller, based on how it's been tuned, what its KP, KI, KD are, its gains, is going to respond with a request for a little bit additional torque. Now, the ultimate, kind of explanation is a little bit more complicated because the system's going to move the way it does. That mechanically, there's really no deficiencies yet. So the torques being delivered to it really are the same. And I'll just kind of put it this way, that this higher torque request to the motor controller, which is now operating a motor with deficient uh, torque capacity, essentially will end up being a higher voltage request, which will drive more current through the coils of that motor, which will ultimately allow it to deliver the requested torque. Okay, so the compensation, I'll call it mechanisms, a little bit involved. Okay, but the main point is because there are controls there, that there is a way that additional current will be requested that will allow that equipment to perform quite well, quite effectively, even though the equipment itself is deteriorating. Okay, so that brings us to predictive maintenance, right? And so I think this is a way that many of us kind of come to the idea of predictive maintenance. What a great idea it is, is that, the equipment does deteriorate, and, a lot of people, watching this presentation are responsible for equipment that, naturally will have some, I'll say, time periods over which it will deteriorate. Okay. And so anyways, the main point is that if you kind of know the condition of your equipment and you kind of know, where failure will occur, that you can look at a chart like this and figure out how much time you got left. Okay. And based on that knowledge, you'll schedule maintenance at some point shortly before, the anticipated failure. And so, it's through your experience and your knowledge of, what leads to, really unacceptable performance from your equipment that you get very good at knowing where this gold dot should be. Okay, so what we're going to really talk about in this presentation is we kind of saw this already, that we realized that all these signals that are being kept track of and that are kind of on our embedded processor that's running controls do reveal the condition of the equipment. At least they reveal something, that things are different and what these signals look like, when there is a motor failure compared to nominal performance. And so anyways, we're going to get a little bit into the analysis of such signals and how we can kind of keep track of them and come up with really good means of understanding the current state or the current condition of our equipment, right? And so you might say that if your job's determining where this gold point is, maybe my job is to tell you where the green dot is, right? And so any good remaining useful life calculation is always fed by a good condition indicator, right? And so we're going to spend some time on that. And that's the main point of this presentation. All right, so let's kind of explain how we got here, okay? And to me, it's really mechanical that is the source of all loads that are encountered in this system. Now, those loads get converted into electrical loads as more current will be needed as we push heavier packages and the various things that can take place, right? So anyways, let's go ahead and close this down and let me explain the mechanical model, right? And there is a tool set that's a bit, that allows you to build these electromechanical systems in terms of what I'll call the physical descriptions, right? That ships with Simulant called SimScape. And a lot of people might know about that already. It's a very useful tool set. And so with regard to mechanics, it's called SimScape Multibody, right? And so the description of a mechanical model, it's really the objects that are in it. I click on this. Here's one of my packages. You'll see that it goes by the name brick. There's one called disk, and you'll see that I click on that here in the list. It shows up right there. And so this is a tool called SimWise, and it's part of our MathWorks Connections partner program. And in my opinion, it's the best way to define any mechanical model that you'll want to run inside Simulant. Okay. And anyways, I like this interactivity that takes place through the list as well as through the physical picture. And I can click on these devices and I can get important information like their mass and so forth. I like kind of pointing out this guy. So notice I'm going to click on this part right here. Right, as soon as I click on it, it shows up highlighted in the list right here. It's got this crazy number name. But I see it's part of an assembly that's called pusher. Okay, and I'm bringing the attention to this only because it's going to reveal a nice little optimization that's good for you to know about. And so I'm going to go to visibility, hide all others. And we'll see that that object is that assembly. And for the main point here is that it's all going to move together as if it's one piece. So as we bring this into Simulink, we'll see kind of how all that works out. All right. Now, the other thing I wanted to point out is kind of the interactivity of this, right? And so that I can kind of click on here, this, and I'll just kind of say that this ability to kind of click, and put in a spring, for example, is quite easy. And it makes it pretty easy to put together a system like this. This probably took me 5 or 10 minutes to do, right? And there are other videos, I'll provide links at the end of this presentation that will take you to them where I go a little bit more in depth to the use of this tool. Okay. Now the other thing I wanted to just kind of bring attention to is that this is a mechanical simulation tool too, all right, and that the device that drives everything is the motor, and we'll see that that's modeled right there. And the only point here is that this is not programmed to really represent the electrodynamics of the motor as well as the controls, which will control voltage, to control the current, to kind of make everything work. And that's kind of the reason you want to bring it into Simulink. Okay, so the overall system model ends up being, well, you end up having the capability to represent it and express it quite well in MATLAB and Simulink. All right, and so anyways, I'm going to just kind of bring this over right now. You'll see this app I created called Get Geometry, kind of working with the developers of SimWise. And I'll click on Import to Simulink, and it'll take that active document. And so you'll see a Simulink model gets opened up with the same name that we had inside SimWise. So it's FlowPack Machine with Spring NC. NC actually stands for no contact. I'll explain that in a second. But what I want to show is essentially that what you see is what you get, kind of nature of mechanical modeling here. And you'll see that there is a motor, which means that there will be a Simulink port requesting torque. Now, we saw that And this is how we're going to implement the plant. Ultimately, the electric motor will deliver a signal, which will be that torque. But we saw that we were using this in the controller also, and so there are two modes in which you can have this, and one will be that you provide torque or force to, kind of represent your actuators, or you provide motion. If I choose motion, notice that the name gets changed to underscore PVA. PVA being position, velocity, and acceleration. It means that you're sending a three-component signal with the position versus time and the first and second derivatives, which would be velocity and acceleration. Okay, now I want to go inside here, and we'll just kind of clean it up a little bit at first. And so I'll just kind of move this spring so it's right up here. I'll straighten out a few of the lines. Okay. And so the natural kind of stuff that's available in Simulink enables you to clean this up quite quickly. And I think the last thing I'll kind of point out here, there is our spring, but let's go into this piece called the pusher and just kind of show how, all those parts were kind of merged together to have one common STL or animation file, as well as the mass properties were accumulated. So there's the mass, and I guess you say parallel axis theorem to accumulate the overall inertia. Okay, so I think that's all I really need to show here. So I want to get back to our model. Okay, and so I want to just kind of point out kind of things that I needed to add to this to kind of get it to work. And we'll get to this in a minute, but there's the electric motor. So let's go inside the mechanical model, and you'll see it'll look a little bit different, and most of it was me adding these contact models between the pusher and the box and the disc, right? And therefore my pusher's a little bit more elaborate as I needed to say create more interfaces. These are essentially the points of contact are defined this way for interaction between the blade of the pusher and the two packages. But you'll see in the solid model right there, it's that same old pusher. Okay. All right. So let's go ahead and come back up to this level. And now I want to just kind of focus on the electric motor and the mechanism. So we saw the mechanism called motor before I changed the name a little bit. So it's motor torque, units are Newton meters, and it's to be provided by what I call the torque electric, which is the torque generated by the electric drive model. So let's get in here. In here, we're going to see Simscape Electrical. We're essentially working with a permanent magnet synchronous motor. This is a three-phase motor, therefore it's got A, B, and C terminals. These are essentially, a circuit diagram. These are ideal conduction paths connecting it to essentially, I'll call it the power electronics, right? And it's through the controller that we essentially regulate the contact with our voltage source to put voltage on these terminals. Okay, so the controller essentially controls every bit of this. And so it's a field-oriented controller, and it takes feedback on like current and angle and angular velocity, and essentially allows you to command a torque that will be delivered by its calculation of the voltages for A, B, and C, right? Now, on the permanent magnet synchronous motor, this is part of Simscape Electrical. It's a physical description of what the motor is. Excuse me. And so sometimes you lose kind of, the mathematical basis, when you use these physical description models. So all these tools provide it quite well through the help dialog, and you'll see the relevant equations and things like that as you go into these dialogues. Now, the thing I wanted to really bring our attention to is that it is an electric motor with certain capabilities, which is essentially associated with, well, I'll call it for the most part, the optimal condition of what the motor is reflected by, simple things like the stator resistance we're seeing here, the armature inductance, and the flex linkage. right? Now, flex linkage, I'm going to just explain a little bit, but ultimately it's a measure of I'll say the magnetic strength that can be generated by the windings of the motor, right? And alternatively, we could describe it in things like torque constant and voltage constants, right? Now, the other thing is that we're assigning these with MATLAB variables, right? And that it's here you'll see how we achieve the motor failure. Now, the motor failures generally, motor burns out because you ran it hot, and you ran it hot by putting too much current through the coils, which generated heat that ultimately begins, I call it melts, but it deteriorates the insulation between, the loops of the coil, right? And so if it deteriorates enough, you essentially have short circuits between these loops, and essentially that short circuit will eliminate the current path that would take you through the coil that would generate or contribute to the magnetic field. And so the nature of the model is that we simply multiply nominal values for resistance, inductance, and flex linkage by a factor we call motor factor. And motor factor, think of it as a normalized parameter. It ranges from 0 to 1, and if it's equal to 1, it's perfect performance, and if it's 0, it's essentially not working at all. Okay. Now, where I'd like to go next, though, is that monitoring or assessing the condition of equipment and assessing what it's capable of. Well, there's a long tradition of doing that, in control development. Therefore, there's kind of this idea of overlap between predictive maintenance and controls that's important to talk about. So, anyways, what I'm going to do is I'm going to kind of show you kind of the identification process, that how we can use data from tests to help us come up with a better model. So I'm going to kind of close down a few of these things right now. Let's clear my workspace. Right. And let's go to this directory with DC motor SPE, right? And so I don't have a permanent magnet AC motor, and so I hope that you can excuse that, but I think that I can kind of show the general process quite well with this DC motor that I've carried around with me for years, and I've done this demonstration many, many times, right? Okay, and so, well, let's just kind of do this, right? And so here's the Simulink model. Yeah, maybe it's a good time to show this, all right? That this is a hardware demo, all right? And my voltage command, you'll see that we process it a little bit so that we can connect with real hardware. So 5 to -5 is the range on which we will apply voltage. We'll take that voltage request, and we'll add 5 to it. So we got a number between 0 and 10. We multiply it by 255, but divide it by 10 to essentially get an 8-bit integer, which will set the pulse width modulation on the onboard, I'll call it power conversion scheme. Essentially, the pulse width modulation is running on this little Arduino right here, and that we communicate with Arduino through a COM connection. So I got this little USB connection to my laptop. Right, so that's the basic idea. Let's go ahead and hit run, and I'll show the run as I run it off my scope right here. Okay. All right, and so hopefully you're not exactly sure what that was. I might run the test again because I don't like it. So let's do it again. Yeah, much better. Okay, so that looks like a good test. And so I will just save that to my workspace. And in my workspace, you'll see that I have these two signals right here. Okay, and so basically cleaned it up a little bit, make sure it starts off at 0 and all that kind of stuff. All right, so now I want to bring up the tool called parameter estimation. All right, and some parameter estimations launched from the model. Right, and the basic idea is I want to compare that data to a simulation model. And so let me convert my representation of the motor from an open loop interface to a Simulink model. And here you'll see that everything changed to essentially a direct solution to the differential equations. So essentially here's the integration, or I'll call the solution to the dynamics of the mechanics. Essentially we'll see things like shaft inertia and damping are important, as well as the electromagnetic torque, which will be the current times the torque constant. And then here we'll see the electrical dynamics, mostly governed or regulated by the inductance, but we'll see resistance as well. But these, again, these are the parameters that really kind of define the state of the equipment, based on its identity being a DC motor. Right. So anyways, let's go ahead to apps, and we will click on parameter estimation. All right, and we'll open up a session. And so I basically put all this together a little bit earlier. Motor 3 Terry session. All right, and we'll see that it's been set up to essentially vary the parameters of torque constant, inductance, resistance, and damping to accommodate the best fit between my simulation model and the data. All right, and so this is data I captured 2 days ago, but pretty close to what we just did. And I'll just go ahead and click on the estimate button. And this basically runs pretty quickly. We got this estimation report, which will kind of keep track of how many iterations we go through. Basically, it's going to run that model many, many times until we get the best fit. And it's going to apply, kind of a classic, optimization algorithm of, following what they call the steepest descents. It's this idea that there's some sort of optimization surface and you're looking for the minimum value, and you follow kind of the trajectories that will get you there most rapidly. Okay. And so, anyways, let's see how well we do with this. All right, and so there's our first representation of the Simulink model, and we'll see it's kind of a far distance from convergence. So it's did that with a calculation of 9 simulations, right? And just to kind of inform you, because we're going to have to wait a little bit for the fit, that number 9 is not an accident. Actually, there's our second iteration, so you can see it closed the gap quite considerably. And you'll see that in the cost function is showing right there. So it went from what? 38 to 5. Okay, but anyways, the basic idea is it perturbs each of these parameters in a positive, negative direction, and so that will be 2 times 4, which will be 8, and they'll add one more for essentially their nominal values. So basically 9 times for each iteration to essentially recalculate the best direction to getting to your minimum. Okay, now part of why I really am going into the depth of showing this, certainly I want to, emphasize the point that through MATLAB and Simulink, that we're able to support, I think, all the simulation approaches that are really available, that you know the system, you derive your own equations, you program a solution. Okay, now we took a shortcut. We physically described it, and we rely on these classic methods for rigid body dynamics and electric circuit simulation and motors in particular to be automatically applied based on our physical description. Well, the last one, of course, is go to the lab, make some measurements, and maybe fit the data. And we typically call that empirical. So we're supporting, all the really key ways of building a useful simulation model. But the other point I really wanted to make, because this is a presentation about predictive maintenance, is the fact that this is a diagnostic, and that what it's diagnosing is what is essentially the condition of the equipment, which will be expressed by our understanding of what K, L, R, and B. Now you notice I didn't include the shaft inertia because I kind of feel like I know that. I have access to the CAD drawings, and therefore I know what the shaft inertia will be. So anyways, I think that this one's almost done. We might hit the stop estimate button, but I think I'll give it, maybe like 15 more seconds. And is that it? Yes, it is. All right. And so we did get to essentially the best convergence, between simulation model and data. And if all I care about is response to big voltages, and let me kind of show you the basis for both the test as well as the simulation. Really it is, if this is an open loop test, what's upstream is really our definition of what the voltages will be. And so we'll see response to these big, steps in voltage is really good. That's what the big peaks were. But we'll see very, very poor correlation early. And all I'll say here is that these low voltage ramps are intended to really kind of incrementally increase current and look for that place where the torque's just enough to break the static friction. And you'll see in some of the demos that I'll refer to at the end, where we do actually investigate this a little bit further. We put in a more sophisticated, what I'll call it friction model, and we're able to get really, really good fits there. All right. So anyways, but this idea that we can diagnose, well, you might be saying, well, why do I even need to do anything but parameter estimation to understand the condition of my equipment? And I wouldn't entirely discourage that, but I'll really kind of point out some real benefits of having some onboard your embedded processor approaches. It will give you more instantaneous information and probably a little bit easier way to get the information. So let's go ahead and shut this down. Shut that down. And get back to our directory with our little mechanism. And I will clear my workspace. And I'll reintroduce my current parameters. Okay. And so what I'd like to get into now is the descriptions of the failures that we set up for exploration, with this model. And the basic idea is through simulation, you can know what it looks like when there is a failure. And we kind of saw that, if the motor is reduced by 50% of its capacity to generate torque, all right? And so I'll just kind of hit run one more time and we'll establish our nominal condition again. Okay, and let's introduce, or let's kind of describe some of the other failures. Okay, so we already saw in the motor, the failure is really defined through the resistance, inductance, and flux linkage, and it's essentially factoring in by this thing called the motor factor. Right, again, normalized parameter ranging from 0 to 1. Okay, now the additional failures we put in, again, I'll just kind of zoom in to cover this area, is the spring, and we created a similar type of factor ranging from 0 to 1 that multiplies into the nominal value of the spring constant. Okay, and then the last one we put in, this one I'm kind of proud of. I thought it was really kind of interesting. Is that what if there is a belt failure? And the basic kind of idea here is that, whoever's working this operation line, maybe they got up early one morning and made themselves breakfast, and they created waffles and put syrup on it, and somehow they spilled some syrup onto the belt. Right? It's a very nice local problem, and we set it up so that it's only occurring with regard to the disk. Right? And so that we're representing kind of that resistance to movement through the internal mechanics of our contact model, which is done through, it's a little technical, but a prismatic joint, so it can only move along this line. Anyways, it's right there. And I called it belt factor, but really it's a direct assignment, and it will be assigned in units of newtons per meter per second. Okay. All right. You'll see that disk contact ultimately is connected with the pink disk. So let's run this now. Oops, let's put in the belt factor of 10, all right? And the belt factor of 10, again, those units of newtons per meter second. Okay, and so again, it's a local belt failure, so the blue package slides off just perfectly, but here comes the pink one. Whoa, and look at that. So that's interesting. And so I'm going to take the scroll and bring you back to here, right? And again, I just want to kind of reveal the animation that we've been looking at actually has been an animation of two disks, right? And one is an animation based on the model that's on the controller, and the other animation is based on the model of the plant. Okay, and so basically the controller thinks that this is where the disk is, but in reality, that's where it is. Okay, and then in a way, predictive maintenance, when you are kind of doing it through controls, is essentially that difference between what the controller thinks it is and what the plant really is. Okay, and so if you can detect that, I think you have a good strategy, and that's the basis of kind of how we're doing what we're doing, right? And so now I want to bring you to some things I captured and showing them in this PowerPoint slide. But I ran, error simulations. We already saw the one for the motor, and that the angle error looks like this, kind of peaks out of 1.5. Well, if I make my spring factor 0.5, we'll see that the error is maybe about zero point 0.8 degrees, and it's in the opposite direction of what a motor failure will be. Now, the one we just looked at, the one with the syrup on the belt, the real sticky surface localized to the pink disc, we don't even see anything. Essentially the green curve is on top of the gold curve, the gold curve's nominal performance, until the very end when we engage the pink disc, and then we see that show up in an angle error. And down here we'll see essentially the torque responses associated with that. All right. And so I want to focus in right here. And just, if nothing else, just say they all look different, don't they? And then maybe we can come up with a signal analysis that will be very good at predicting, what the current state of our equipment is. All right. So, anyways, I'm going to take you back to the model. Let's get into the controller, right? And didn't really, again, this is all on the controller, so these are calculations that are fair game, that they can be converted to whatever, C, C++, or whatever, and put onto the processor with the direct kind of access to all the instrumentation of the equipment. Therefore, it's informed continuously. And so these can be live calculations. And so for the run we just did, actually, let me explain it a little bit better. All right, that we're taking angle error, we're doing some processing that's taking place in here. It's calculating or estimating the spring constant. Here we divide by the normalized or the nominal value of spring constant, and hence we come up with essentially an estimation of the spring factor. Now I know that spring factor was equal to 1, so it certainly worked very well for that. So now let's go make the spring factor 0.75. And this time let's run the model from this scope. And we'll see it starts off with a value of 1, but after 1 second, we're almost there, it recalculates and absolutely gives us the value that we were expecting to see, 0.75. Right, so now I go into the block a little bit and explain to you what's going on with this. Right, and so, angle error is coming in. We're going to square it. We are then going to integrate it with respect to time, right? And then this signal is sent into essentially what I call a snapshot. And so this is what they call a triggered subsystem. And at 1 second in time, it will essentially capture that value and it will report it into a lookup table, essentially matches spring constant value with what this signal represents. And just to be very specific, that this is, this is an RMS calculation, which would be square the signal, integrate, and then divide by the integration time. So essentially we're not dividing by 1 because we don't need to. All right. And I'll just say it this way. It works fine, even if there's a belt factor of 10. Um, but what about the motor factor? And the belt factor being 10, we know that all that happens way past 1 second. So that's kind of obvious if you give it a little bit of thought. but let's put in a motor factor of 0.5. Right? So we'll rerun it one more time. So again, it starts off at 1, and it's at that 1 second that adjusts. And clearly, it gives us a wrong calculation because we know that our spring constant is 0.75. So the only point here is that things get a lot more complicated, if there are multiple failures occurring, right? Right, so now I want to bring you to a really cool tool that's part of kind of giving you my, well, let's get it here. This is kind of the most interesting place to start. Um, Really cool tool. It's called the Diagnostic Feature Designer. It's part of our predictive maintenance toolbox. And what it allows me to do is to run the simulation many, many times, right? And so I ran essentially 121 simulations. And so I varied the the motor factor from zero point 0.5 to 1 with increments of 0.05, so therefore 11 different values of motor factor, and I did the same thing for spring factor. So 11 times 11, that's 121, and so all these curves essentially represent the angle error that's operated upon by the PID um, for 121 simulations. Okay, and this image I think is really great. So in orange essentially are failures, and blue are successes, according to my definition of, explain my definition of success in a moment too. And what I wanted to really get at, as I zoom in here, is this looks really hard to do for me. I don't actually know how to do this, and we'll see that as we go through this. And it's that these are failures are very much interlaced into some of the successful runs, and how you can design a feature extraction for something like that's probably beyond me. Okay, but I want to kind of show you the overall process. And the overall process was, well, I showed you that I did an RMS calculation, worked real well if my motor factor was equal to 1, right? So you'll see one of the options here is RMS, but you'll see other things like mean calculation, standard deviation, some things that I don't really know that much about, like shape factor and skewness and kurtosis. I mean, I can understand them a little bit by like going to Google and things like that and learning about them, as well as my colleagues, you know, uh, who know this kind of stuff quite well. There's people that I work with who specialize in this, and so they're great resources. And certainly, if it is of interest to you, we can connect you with them too, right? And you click on OK, and it essentially calculates histograms, right? And so blue is success and orange is failure, and these are histograms, and therefore, if I'm doing something, like right here's my RMS calculation. Whatever the value is essentially binned up. It's put in buckets. That's the idea of histograms. So if it is a value between a certain range of here and here, it gets put in that bucket. And so you cross correlate this thing with success or failure, and essentially, you know, you're looking for something, some sort of feature like RMS or something that essentially separates the blue bins from the orange bins quite well. And the only one that really does it super well, that's not bad for RMS. I think the best one here is mean, which is that one. But you'll see that, that my parameters for really defining the simulations, they're provided to the same analysis. So even though spring constant isn't truly a measurable thing, it is available for this type of analysis, and you'll see it's beautiful at it. The blue bins are very much separated from the brown or orange bins. The only problem is that it's not measurable, okay? And that we need a signal that we can process that maybe can correlate with this and reveal success or failure. And part of why the spring constant does so well is my definition of success versus failure was very simply associated with the spring constant. I basically said if the spring is operating at 70% capability as defined in its design, then I call that a success. All right, so it couldn't help but be successful. And so that, as I rank these features, you'll see the spring constant, of course, does really well. And the next best one is, it is the mean, and it only operates at about 60%. All right, and so anyways, probably not good enough. All right, and so here's kind of the idea that I came up with that I'm capable of. And my idea was Well, let's limit, you know, the deterioration of the motor to something much less than 50%, right? And so I basically ran these same sets of simulations with only a 10% failure. Let me give you a little bit of an indication what this really is that we're operating on. So let me just kind of copy that name and paste it in right here, right? And you'll see basically 121 simulations, which are captured in these timetables. And you'll see the variation of spring constant and flux linkage that takes place, right? So we'll get a little bit more into this in a moment too, but let's go ahead and use it now. All right, and so go relaunch the diagnostic feature designer. Okay, let's import the data. Notice it's reading in that 10% one. Okay, now I'm reporting spring constant flux linkage and whether or not it succeeds or fails through a fault code. The fault code is either 1 or 0, and I need to tell it that that's the condition variable. And I click on next and import, and it'll bring all this in. And essentially, you know, most of what we just were looking at is reported through this thing called the feature table. Now, as we go in and create some of our own features, we'll just add to this, and we'll kind of see that the feature table is kind of the data set that's kind of keeping track of everything, right? But I always think it's a good idea. Let's look at the signals. Again, reminding you, degradation of the motor as expressed from flex linkage only goes 10% below its nominal value, right? Now I want to show or group by fault code, and this is what I want to see, okay? What I'm seeing now, I think I'm very capable of dealing with, right? And what I'm seeing is a nice grouping of success versus failure. There's a little bit of overlap there, but for the most part, the higher amplitude of the oscillations are associated with failure, and I expect things like RMS should be able to capture that pretty well. So let's go to feature designer. Let's select all those ones, and I always, well, whatever. I'm going to remove the signal processing metrics like signal to noise ratio and so forth because I don't think they're relevant, and the other ones seem to be pretty good. So let's click on OK. And essentially, it's processing all 121 simulations for essentially the signals that are represented in this picture, and it's going to create those histograms. And so this is beginning to look a lot more promising. You can see for sure RMS looks pretty good. The blues and the browns are pretty nicely separated. I think we're seeing that in a few things. Peak value looks good, and again, we have our spring constant information to use as the basis of assessing how well we did. So let's now rank the features. And ranking operates on the feature table. Okay, and this is really good news. It's even surprising to me. Look at that, spring constant comes in fourth, and I'll just say there may be some kind of crazy numerical quirk that I don't understand. It seems to me spring constant should always be the first one because the definition of failure or success is directly defined by the spring constant value. But what's promising is that there are at least three, I'd say there are at least four really good ways to do this, including mean, RMS, standard deviation, and then the peak value. All right. And so to me, that means I can put a block inside my Simulink model that will end up on the controller that will do those analyses and be able to tell me with confidence what the spring constant would be. And it is constrained by the idea that the motor cannot deteriorate beyond 10%. And, you know, whether or not that's acceptable for you or not, would dictate if you could choose the path that I did. If not, then I'd encourage you highly to talk with us a little bit more deeply with regard to how you might apply, I'll call more sophisticated methods of deep and machine learning to get it to work. Right. And so anyways, you then just kind of export these, and you can export them to a thing called the classification learner. And that's kind of, I think, a means to upping your game on these more sophisticated methods. Okay, so the next thing I want to show is how we got this, all right. And it's pretty simple, and it's only take us probably a minute or so, right? And essentially, this is all generated by um, a script I wrote called varying the constant and motor factor, right? And three or four main points. The first one is it's only 32 lines of code, so it's fairly simple what I'm doing. It does call on this one function, again, a very simple function. It is essentially going to generate the arrays of values for spring factor and motor factor and belt factor. Now you'll see that my choice on range, well actually range for spring factor and motor factor is 0 to 10. That's 11 values, 0, 1, 2, 3, all the way up to 10. And that I chose a single value for belt factor. So 11 times 11, that's 121. Okay, now the main point is to set these up and then to run some for loops that will run one of my favorite commands, which is the sim command right there, right? So that essentially is your means of writing a MATLAB script or function that will run your Simulink model for you. And I think I'll get a little bit into this. Some of you who are watching this, I think you kind of a lot of customers on the West Coast may know my colleague Yoke Peng. And Yoke Peng is a wonderful resource and very helpful in many ways. And so anyway, she's saying, what your way of doing it, is not the way you'd want to do it as you get into like parallel processing. And so the idea of parallel processing is the idea of kind of being able to batch up everything you need to do to essentially distribute the many calculations that you want to do onto a cluster. Yeah, and the fact that I just put together like a desktop machine in the last year, and I used an i7 processor with essentially 8 processors, means that I could essentially run it on that machine and it'd run 8 times faster, pretty close to 8 times faster. And so the idea of doing that is very nicely enabled by this idea of batching up your simulation. And so it's this object that's available, simulink.simulation input. And I'll just kind of go to help on it. And uh, again, just kind of refer you to this. And I won't get into too much detail, but it's in this object that you define all kinds of things, like model parameters, our parameters, of course, being motor factor, belt factor, and so forth. Okay, so anyways, let's get back to the topic of the script. And so we talked about essentially varying spring and motor, but keeping belt constant, embedding it in these for loops. So it'll take us through all the simulations, and then essentially the creation of the data table. I am going to point this out because this was something that I had to get help on. Let's see if I can quickly get to it. I think right here will do it for me. Yes, it does. Okay. And what I wanted to show was what these timetables look like, and I'm only showing the first 10 elements of the first simulation. And so anyways, a timetable is essentially 2 columns. First column is time, and notice this. It expresses in units of seconds and then the value of the thing that's compared to it. Well, in our case, the PID or the angle error is what's represented by that column. And I'll just kind of say that it's not a hard thing to put this together, but I really didn't even know how to do attachment of units until I talked to somebody at MathWorks tech support, and they told me about this command called seconds. So anyways, the last thing to bring attention to in here is my very simplistic definition of fault. And it's essentially equal to 0 if the spring factor is greater than 0.7. It's equal to 1 if it's less. And, most likely you're going to create fault code 1, fault code 2, fault code 3, and you very simply kind of make that selection as you begin your analysis with the diagnostic feature designer. I highly suggest put a fault code on the motor factor, probably on the belt. But I'd also say that there are going to be things that are measurable in your model that probably provide really good potential for a useful fault definition too. And so I'm going to go back to my model and kind of show in my plant for the electric drive the stuff that I got going on down here at the bottom. All right, And so we'll see, essentially here's the line on the ABC current. All right, so essentially a signal with three values, current A, current B, current C. I'll show you what it looks like, for our system. Here's pushing off the first package. Here's pushing off the second package. That's what these all represent. Here's essentially the first move where we retract the thing into kind of its baseline positioning. Okay. Um, Anyways, you'll notice that one of well, I think I'll come back to this in a second. All right, so that's ABC current. We're taking ABC voltage, we're sending it into this block, and here I'm using a block that comes with SimScape, which will take that ABC voltage, ABC current, and it will calculate the what's it called, the active power and then the reactive power. Now, reactive power is essentially, power that ends up being kind of stored in the magnetic fields of inductors or the electric fields of capacitors or, that sort of thing. And so it's really kind of conserved, and so it's not really consumed. But active power, that's really the power associated with really kind of doing that work, moving those packages off the conveyor belt. And so I take that active power and I integrate it with regard to time. And for the simulation we just ran, it ends up looking like that. Okay, all right. And so then the other thing I thought about, well, how do motors really fail? It's because you drive too much current from them and you ultimately melt the insulation. So it's a good idea to track current. And according to kind of the geometry, it turns out that that second, the B current is the one that reaches the biggest peaks. And so I decided to keep track of that one too. All right, so I'm going to go back to my PowerPoint slide and we'll just kind of wrap up on this point. All right, and anyways, what you'll see here, this is what we've been looking at a lot throughout this presentation, but that's essentially angle, versus time. There's the motor failure. In gold is I'm only showing three failures, or two failures here. Gold is the nominal condition and blue is the spring failure, right? And so here's the energy consumption, right? In a way, this necessitated me to really think about current, because all of a sudden I was saying, is the spring really needed there, right? And what I mean by that is that the motor failure energy consumption is clearly a problem. As the motor deteriorates, it needs more current to generate the same magnetic field, and that ultimately ends up with a larger power consumption, right? The gold then represents nominal conditions, and then the blue, spring failure, actually reduces the power requirement. Now, I think that might suggest maybe redesign this a little bit and don't, let the motor maybe hold a position that's working against the spring. But that's a different seminar, a different presentation. Um, but it made me want to kind of explore why is the spring there anyways. And so I think you see it in the current. And again, it's that B current for all three failure mechanisms that we're showing here. And I'm just going to zoom in on this. And we'll see that if there is, and there likely is, a maximum current threshold, at least an amplitude, that you shouldn't violate. Well, the loss of a spring constant actually can lead to that type of violation. Okay, and the spring's there to essentially help push it when the movement of the pusher is encountering a package. Okay, so anyways, I'd say that with regard to your definition of failure, nobody defines that better than you do for your equipment. You understand, your own requirements and what is good performance versus bad performance. And probably the bigger point, the one that I really want to make sure is clear, is that these are very rich models as you put mechanics and electronics together. And I think you'll be amazed by the things that you can include in your simulation and anticipate, kind of their impact through detrimental things like over consumption of energy or maybe currents that can lead to insulation breakdown. Right. So anyways, with that, I just want to kind of wrap up. I made reference to previous videos I've put together. I'd suggest if you like what I did on the mechanical and electrical modeling, you'll see much more in-depth demonstrations in these two links. So mechatronics with MATLAB and Simulink. You'll find both of these both on the MathWorks website as well as on YouTube. I think the second one has like 31,000 views right now. So they've been pretty popular. I think both, though it's in the thousands. And this one here, it's like a 10 to 11 part series that kind of breaks it down maybe in a very nice logical way. Um, Now, as I kind of referred to, we kind of ran into my limits to do deep in machine learning, but certainly I think I made a case for doing it and including it on your controller in your Simulink models, which will ultimately get you onto the processors. And so my colleagues in Italy did some really good work where they do use the classification learner and they do much kind of better diagnostics or feature design to really get more specific in what values of failure parameters or condition indicators are when multiple failures are occurring. And so, I can, my main point here is in their data generation video,
Hi, and welcome back.
you'll see that they are working with the same piece of equipment that I have been.
Flowpack
Yeah,
machine
there it
should
is, right there,
behave.
doing a little wiggle. Doesn't have the belt and all the stuff that I added to it. And anyways, we are doing a seminar that I invite people to if you still have time to come to, where we'll get into this too. All right. So, anyways, just kind of wrapping up. I tried to present this from kind of my own personal perspective. And I view that people like myself, they really have quite a bit to offer to this area of predictive maintenance. And this video, I think, probably presents it through the Simulink workflows, probably a little bit, well, probably way deeper than most of our presentations on predictive maintenance. And so I think Simulink has quite a bit to offer, and I think marrying this into kind of the control design workflow will serve you quite well. Um, I would highly encourage, kind of all these things I'm showing, that there is the difference between like onboard analyses of signals that generate features that can be very predictive, that give you very instant information, and that's kind of what we did with the diagnostic feature designer. But then I certainly say kind of go to these workflows that have been kind of there for a long time for the purpose of developing really good controls like parameter estimation and so forth, and kind of use that the best way you possibly can. So, um, and then ultimately it is being developed through Simulink, which supports a code generation process that will probably help you quite a bit on getting it onto the controller. So, anyways, thank you very much for watching this presentation, and I'd love to hear from you. Thank you. Goodbye.